Thanks everybody for coming out to Tech Talk tonight. I appreciate you carving out some time in your evening to hang out with us for a little bit. I'm from Bodybuilding.com, as well as the speakers you're going to hear tonight. And we really hope that you learned something and there's a good dialogue. We're going to have two speakers. The first one will be Ryan Deering. He'll be coming up here in a moment. So the format will be 30 minutes or so of some presentations, and then we'll have an open Q&A session on each topic following the presenters. And then we'll do about a 10-minute intermission in between the two speakers tonight. So without further ado, welcome, and thank you so much for coming tonight. And I'll turn it over to Ryan Deering.
All right, can everyone hear me? Good, cool. So I'm Ryan Deering. I'm the engineering manager for our community API teams at Bodybuilding.com. So what I have up here, we're having a little bit of technical difficulties, but this is our Hystrix dashboard for production servers. And so normally this would be updating very quickly in real time, and you would be able to see exactly what's happening on our production servers right now. This was actually running over David's phone, and he uses Verizon, so apparently we shouldn't use Verizon in here. All right, so let's get started. So our REST APIs are at the lowest level of everything we do at bodybuilding. So even if you go to our website, our native apps, anything you do on our site, whether it's via your phone or your browser, is at the bottom going all the way to a REST API. And so our current REST API is doing over 110 million API requests every day. So to handle that traffic, we have hundreds of servers, which means we have hundreds of dependencies. So each of those servers, they're application servers, cache servers, database servers, they all depend on each other in some way. And so when you have that many servers and that many dependencies, you're pretty much guaranteed to have things fail. So we need to account for failure and plan for failure. And when you talk about networking and systems, we've pretty much figured this out, right? We have load balancers and dual power supplies, even down to like our circuits, right? We make sure all the servers are on different physical circuits so that if we lose power. But when it comes to software, that's a much harder problem to solve because there is no one-size-fits-all solution. It's always going to depend on what your application is doing. So if you're writing an application that needs to go out and get accounting information and that call fails, you're going to handle that differently than if it's just getting the latest stock quotes. So we need to figure out how can we make our applications more resilient. So what do I mean by having a resilient application? So a resilient application should be able to dynamically adapt at runtime to unexpected failures. And in addition to being able to adapt, it needs to maintain some level of performance. It doesn't do us any good if our applications keep running, but they take 30 or 40 seconds to respond to every request. We also need to make sure that we prevent cascading failures. And so if you lose a database, for example, you don't want to lose all your APIs and then all of your web servers, and eventually you have an entire system outage. So we want to make sure that failures are as isolated as possible. So to do that, we can fail fast and fail gracefully. So failing fast means if we know that some call is likely to fail, probably because it's been failing a lot in the past 5 minutes, for example, then maybe we should just not make the call. So if a database, for example, is struggling and starting to fail, at some point it just makes sense to stop contacting the database, give it some time to recover, and then contact it again at some point in the future. And of course, failing gracefully means that if we are going to have failures, we should try to do them as gracefully as we can. So that may mean sending up a default response, or maybe a stale cache, or at least telling the user something nice that we were unable to process your request versus like an exception that has a big SQL statement that we couldn't run. And once we've built the system that's dynamically adapting at runtime, we're going to want visibility. Because what happens if our system is up, but it's failing gracefully and failing fast 90% of the time, right? We're going to need to know that that's happening so that we can deal with it. So this photo, if you're unfamiliar, is a tardigrade. A tardigrade is considered an extremophile, which I recently found out about. This particular one can survive in space, like just in the vacuum of space, even in boiling water and freezing water as well. So it's like a textbook example of resiliency. So what are some patterns that we can use to add resiliency to our applications? The first one is bulkheading. And bulkheading is a term that you frequently find in shipbuilding. And what it means is when they build the whole of the ship, they're going to build it in compartments so that if one compartment fails, the other ones are unaffected, and overall your ship stays afloat. And so we can do the same thing with our applications. We can make sure that we compartmentalize not only the applications, but the internal pieces of each application so that if they fail, the other pieces are unaffected. And a lot of us already do this to some degree today. If you're writing something that's connecting to a database and the database is down, you're very likely to get a connection refused exception, right? Which is likely to be a checked exception, or maybe you've thought of it and you've caught that exception and you've handled it. The issues that are harder to deal with are latency. So what happens if you write a query, a database query, you make sure it's optimized, and it takes 50 milliseconds to run, everyone's happy with it, you ship it to prod, and everything's great for months. But then something happens to the database. Maybe it gets overloaded, maybe a drive fails, and so now we're in degraded RAID. But whatever it is, that query that used to take 50 milliseconds is now taking 5 or 6 seconds to respond. In that situation, it's much harder to deal with, right? Because there's no normal, consistent way within Java to say this block of code should run for at most 2 seconds before you stop waiting. And so we need to have some way to deal with that. So if we don't deal with these issues and compartmentalize them, in particular latency, we can have cascading failures or a domino effect where other pieces of the application fall over as well. And so this is a demonstration of exactly that. So you have these application servers that are all calling this dependency, and the dependency starts having issues, and everything that's calling that dependency starts hanging, waiting for that dependency to reply. And eventually those things fall over. And we've actually experienced this in our prod environment where we have a set of API servers that have a number of endpoints, and one of those API endpoints used a database that slowed down. And so what would happen, all the requests that went to that API endpoint, which was typically very fast, started taking like 10 or 20 seconds to reply. And so what happened was we had all these requests coming into different API endpoints, but the ones going to the slow one kept stacking up. And so if you pulled up like our Tomcat status page, you have a limited number of request threads to handle requests. And what we'd see was all of the requests were waiting on that one slow API endpoint, which means we had no threads left to handle requests to the other API endpoints, and now those were down too. And they were down purely because we had no request threads. They should have otherwise been unaffected, and so we want to make sure that we prevent that from happening. So another pattern we can use to accomplish this is the circuit breaker pattern. The circuit breaker pattern works just like it sounds, just like the circuit breaker in your house. It basically means that if we go beyond some threshold of errors or timeouts, at some point we should just open the circuit and stop letting things flow to that dependency. And so we'll just fail immediately, we'll fail fast, and at some point later we'll try it again to see if things have recovered. So as I mentioned, this pattern is an example of failing fast, and it also prevents us from overloading our system. If your database is starting to be slow, it doesn't make sense to keep hitting on it and keep trying to run queries against it. And so when the circuit opens, we'll actually back off of that database. We stop running queries for a period of time, and we give it a chance to recover so that we don't overload the system. And so we don't want to keep loading the system until that happens. So how can we do this? So we know the patterns that we should use, but how are we going to practically do this? So that's where Hystrix comes in. And Hystrix is a library by Netflix that they've open sourced, and they've run into this problem, and this is their solution. And luckily for us, they've open sourced it. And at least for me, whenever I've typically thought of companies that have large APIs, I would think of Facebook and Twitter and Google. But Netflix really has a ton of API infrastructure because they support so many devices. Most likely every phone in the room could get on Netflix right now. And so for them, it's critical that they isolate failures so that they don't have an entire outage. So one thing before we talk about Hystrix to know is that it uses the command pattern. And so the command pattern, as you know, is a very simple pattern. It's just a class that does one thing. So you new up this class, you can maybe pass in some arguments, and then at some point later, you'll run the instance of the class. It will do its one thing and return the result. And so Hystrix does everything by using the command pattern. So using Hystrix, we get the ability to time out slow commands. So commands that are taking longer than usual, we can actually time them out and stop waiting. And we can also rate limit the number of concurrent commands. So with that query example that I gave, let's say that we've tested that query and we know that we can only run 100 of them at a time. Beyond that, we start to take the database down just by sheer volume. So with Hystrix, we can actually rate limit the commands that are running that query. And that also helps us keep our resources in check. Resources are limited, and so we can use Hystrix to say these queries that are kind of unimportant get a limited set of resources, and these other queries that are very important get more resources. So Hystrix also has the circuit breaker pattern. So if we are timing things out, rate limiting them, or they're having errors, we can open the circuit and start failing fast and stop having those commands run for a period of time and give things time to recover. And one of the most powerful features of Hystrix is the ability to do a fallback. And a fallback means that if you try to run the command and we can't run the primary mode of the command, so making a query, for example, we can try and get the data some other way via a fallback. And so that could be using a stale cache, it could be returning like a default value, and we use this pretty heavily. So as an example, if we try to get someone's profile picture and that call fails, we can just return a default avatar, right? It's just a silhouette of a person, instead of having like a broken image or failing the call entirely. We also use this for our profile API. So our site is a social networking and e-commerce site. And so everything we do depends on having profiles. And so when we can't have profiles, we're pretty much down. And so we want our profile system and our profile API to be as resilient as possible. And so if there's ever a scenario where we cannot get a profile from the authoritative data source, we actually will fall back to our Solr cluster that we use for searching, which has a copy of the data. It's not authoritative, so it might be out of date, but returning out-of-date data is way better than being down and returning no data. And one really nice thing of Hystrix, which I had up at the start, is the dashboard, which is a real-time dashboard so that you have visibility into what your system is doing. And Hystrix works really well. These patterns for opening the breaker and timing out commands work really, really well. And if you don't know when that's happening, you could run into a scenario where every command is timing out or every circuit is open and you don't know about it. So having the visibility is critical. So here's a flow chart for how Hystrix works. This looks a little bit busy, but we'll dive into each piece and you'll see that it's not so complex. So every Hystrix command can be run synchronously, just like a normal method call, or it can be run asynchronously, so you can get a future or an RxJava observable and check on the result at some point later. So once you have a Hystrix command ready to run, Hystrix does a couple of internal checks. First, it's going to say, is the circuit open? If the circuit's open, it means there's been too many errors or too many timeouts in the past number of calls, and we're going to fail fast for a period of time. So if that's the case, then Hystrix is going to run your fallback, if you've implemented one, and return that result instead of actually running your command. It will also check to make sure that there's a Hystrix thread available to run your command. And again, this is how we can kind of rate limit and manage where our resources go inside of Hystrix. If there's not a thread available, then it will run the fallback and return that and not run the command. If both of those checks pass, which means the circuit's closed and we do have a thread available, then Hystrix is going to run the command. And so, of course, that has a few possible outcomes. Either the command will run successfully, which is easy, we just return the result to the caller, or it could fail, has an exception, in which case that counts towards our error threshold, and if we get too many of those, the circuit will open. And in that scenario, we'll also run the fallback and send that back to the caller. Or it could time out, which also counts towards our threshold of opening the circuit, and we'd run the fallback if you have one. So for each command, if you've implemented a fallback, there are two possible things that can happen. Either your fallback works, and we return that result to the caller, and the really useful part about fallbacks is that the caller doesn't need to know that the main command didn't run. It was really the fallback that ran, but the caller never needs to know. As far as he's concerned, everything works successfully and things continue on like normal. And that's really where the power comes in with Hystrix. If the fallback itself has an exception, then of course there's nothing else we can do. So in that scenario, we need to bubble up the exception to the calling code so that they can deal with it. And then there's also the possibility that you just didn't implement a fallback. So some commands don't have a reasonable fallback. So one for us is a login command. So literally if you're trying to log in, we have a Hystrix command. If that fails, there is no reasonable fallback for us. So we let that bubble up and just notify the user to retry. So here's a very simple hello world Hystrix command. You'll notice that it's extending the Hystrix command base class, which takes a generic type so that you know what the return value will be. So in this case, it's a string. And you'll see that we're overriding the run method, which is an abstract method defined within the Hystrix command class. And so you have to implement that, and that's the heart of your command. That's going to be the one thing that it does. You'll also notice that our constructor, that we're passing in some information to the super constructor. And this is our simplest case here where we're just passing in a group key. And a group key is a way of grouping your Hystrix commands so that you can say all of these commands are profile related and all of these commands are related to workouts or some other thing. And that's, again, how you can pick your thread pools and figure out how you want to spend resources. So in that example, we will give more resources to profile calls than we will to workout calls because profile for us is much more important. So once we have a command and we've newed up an instance, this is the way that it can be ran. So one of three ways. You can do it synchronously, so just like a method call, calling .execute, as you see here. Or you can call .queue, which will give you a future, and you can check on that result at some point later. Or you can call .observe, which gives you an RxJava observable. And again, that's asynchronous, so you can check on that result at some point in the future. So here's a command that always fails. If you notice, our run command is always throwing an exception. And so every time someone runs this command, it will actually fail and eventually actually open the circuit as well. But because we have a fallback, the fallback is going to run every time. So if you were to new up this class and run it, you would not see a failure. The code that uses this command would never even know that there was a failure. Instead of seeing hello world, it would see hello failure world because that's what our fallback does. And that's where Hystrix becomes so powerful, is that all the code that's using this doesn't need to know that there's some internal issue that's happening. So this is an example of a command that fails silently. And so by failing silently, we mean that it's going to return something like null or an empty collection. And it's essentially saying the command failed, it's not worth bubbling up an exception, but we also don't have some other cached or default value to give you. So we're just going to say we couldn't get it. And this is actually really useful. So for us, we have a legacy profile endpoint that gets all your profile information. So important things like username and profile pic and profile URL. But it's an older API, and one of the things it was also returning is the number of times you've worked out. And of course, that's not critical profile information. And so before we added Hystrix, if we couldn't get your workout count, or if that was taking a long time, then that call, the entire profile call, could potentially fail or take a really long time to return. And so obviously, we don't want that to happen. If we can't get the number of times you work out, we should still return you the rest of the data. And so the way we accomplish that is we wrapped that get workout count call in a Hystrix command that returned a silent fallback. And so in the scenario where we couldn't get the workout count or it times out, we return null. And if you picture the JSON response, you would have all your other profile information, and the workout count would just say, the workout count property would say null, which is our hint that we just couldn't get that value, and you should go to the workout API, which is the authoritative source, to get that data. So here's a command that is doing a stubbed fallback. So a stubbed fallback is the profile picture example that I gave, where there's just a reasonable default that we can always give out if the command fails. And so again, like for us, it's a default profile pic. It could be a different set of recommendations, workout recommendations, and things like that. So this comes into play in a lot of places as well. And all of these, by the way, are in the Hystrix documentation on their website, all of these examples. So if you want to read more about them or run them, you can find them on their website. So one feature of Hystrix that's not directly related to resiliency is request collapsing. So we now have created all these Hystrix commands that do single things. So for us, there's an important one that gets profiles. It takes a user ID, you run the command, and it goes and gets the info on that profile. And we run that a lot. Everything we do needs profiles. And so what we have is all of these commands running all the time. We have hundreds of them at any given time running. And with request collapsing, you can use Hystrix to say, take a small window, say 10 milliseconds, and take all those individual commands and collapse them into one aggregate command. And of course, Hystrix doesn't have enough domain knowledge about your application to do that on its own. So you have to write some supporting code to help it understand how to take individual commands and turn them into an aggregate call. And so for us, that code takes all those commands, makes a call to an endpoint that takes a list of user IDs and returns them all at once. And the cool thing with this feature is that you can then take those and you would say, okay, the caller that wanted user ID 1 would have got this value. Whoever wanted user ID 2 would have got an exception. And user ID 3, the caller who wanted that would have got just null. We don't have a user with that user ID. And so you don't lose the ability to give all the various return types, whether they're exceptions or null or an actual response when you do collapsing. And so we tested this. We created 60 threads, all getting profiles as fast as we could. And when we turned on collapsing, it doubled our performance. And so it's definitely very useful and worth knowing that it's there. So I mentioned the dashboard, which is how we get our real-time visibility into Hystrix and everything that's happening. And it's a very concise way to see all of your commands and what they're doing right now and when they're failing or timing out or having issues. And so we can dive into these and see what all the numbers mean. So this one is again from the Hystrix documentation. This one's doing about 20,000 calls a second. We don't have any that are doing quite that much. We're about 5,000 a second, I think, for our fastest one. But there's a lot of data here. It's all very packed in so that you can have a lot of these on the screen at one time. But the left side with the circle and the line graph, that's showing you over the last 2 minutes how many requests you were getting, so request rate. And the numbers on the right are showing you how many commands succeeded. So the green number is how many had succeeded. The yellow number is how many had timed out. The purple number is how many were rejected because we didn't have an available Hystrix thread to handle them. And again, that's just managing our resources. So we didn't have enough resources to handle that. There was too many running at the same time. So some of those just got rejected because we didn't have a thread available. And then you have numbers on how many are running per second, and percentiles, which are telling you how long your command is running. And percentiles for us are very, very useful. A lot of things will give you the average, and the average response time is, in a lot of cases, not very useful because it's driven very low by cached calls and calls that are really fast. And so for us, it's really important for us to know how long are calls taking that are uncached. And with an average, we can't get that number. With the percentiles, we can always look at our 99th or 99.5 percentile and figure out how long our uncached calls are taking. And that's very useful for us to figure out where we need to spend time improving performance. So I want to show what Hystrix does when we're having some failures happening in prod. And so I took this screen grab right after we were putting Hystrix in prod. We were actually still just canarying it on a few servers, and we had a database who started slowing down. It was getting overwhelmed with queries. And I took this screenshot. This is an internal tool that shows us all the long-running queries on the database. And initially when I pulled this up, it was just completely red. So we had tons of really slow queries. This was as things were recovering when I actually had time to start getting some screen grabs. But I want to show you what Hystrix was doing while this was happening. So as you can see, we had a number of commands that were failing. We had some circuits open for some of these commands, and we were timing out commands. So if you look at the logged in command, there were a number of those that had timed out. And multi-profile pick, 35 of those were working and 29 had failed. And we had only put this on a couple of servers. So now that we have it everywhere, we've had events like this happen again. And what we'll see is all the non-critical things start to back off a little bit, so they'll fail fast. So things like workouts and some of the more obscure features of the website. But the core features, the profile features and things like that keep working. And that's exactly what you want to see Hystrix doing. And so the alternative to this, right, this is showing us that some were failing, but some were succeeding. The alternative, if we hadn't used Hystrix, was everything would have failed because we would have just been sending everything to the database server and it would have fallen over just because of sheer volume. So we have a number of lessons that we've learned from using Hystrix. One of the first ones is it's good to organize your code from the get-go with Hystrix. If you want to retrofit it, it's certainly possible, but it's going to take a little bit of work to refactor things, especially if you're using like Spring injection and Spring dependencies. You'll probably have to refactor some of your code. And so anything new that we write, we always know that we're going to use Hystrix, and so we think about that from the get-go, and we know how our commands will work and where they'll be. We also really like using Hystrix in our internal API libraries. So the API team writes the API server, but they also write Java client libraries for our internal team. So people that are writing the web tier will use our clients. And so by putting Hystrix in that tier, all of those web servers benefit from having Hystrix, and we benefit from having them all back off of failing API endpoints at the same time. And so all the web tier developers have to do is use our library, and they automatically get Hystrix, and they can use a dashboard to see what's happening, and they can tune it and back off if we start having issues. So one thing to know about Hystrix is it's really nice if you have some historical data around the places you're going to put your commands. So you need to know, for example, how many requests per second you're doing, how long do they take, because you're going to need to tell Hystrix what the timeout should be. Is the SQL query going to run for a second or 2 seconds? What should the timeout be? How many of those can we run at a time? And so if you don't know those, you're going to have to try and figure them out and make some educated guesses. And so we've been in both situations. In some cases, we had really good measurements and we knew what our timeout should be. In other cases, we didn't know. And so typically what we've done is we'll put those in production. We'll pick some values based off testing that we think makes sense, or we'll put them in stage rather, and then we'll do a load test. And based off of that, we'll tune them, and then we'll go even more conservative. So we'll make the timeouts just a little bit longer. We'll add a few more threads for using those commands. And then we'll put that in prod and canary it on just a couple servers. And then we can watch that for a period of time and start dialing in what those timeouts and thread pools should be. And so you definitely don't want to put things in prod with the timeout too low or not enough request threads, because your system will starve and you'll start having, in our case, APIs and website pages that don't respond, right? Because Hystrix is timing things out too quickly. So a minor one is that command instances should not be reused. So when you new up a Hystrix command and you run it, you can't rerun it. There's internal state. So if you need to run the same command, you need to new it up and run that new instance. And a really big one is knowing your fault versus non-fault exceptions. And so what I mean by that are there are certain exceptions that are not error cases in the system. So a good one might be if someone tried to get the profile for a negative user ID, say negative user or -1. That's an invalid user ID, and so you're likely to get an exception that says invalid user ID. That should not count towards our exception threshold, right, of opening the circuit. Otherwise, we could potentially have someone that just keeps requesting -1, and now the circuit opens because as far as Hystrix is concerned, we're having all these errors that are throwing exceptions. And so Hystrix has a way to deal with this by wrapping those exceptions in a bad request exception, which tells Hystrix this is just some kind of validation issue and should not count towards our threshold for opening the circuit breaker. But you need to know what those exceptions are going to be and think about them before you put Hystrix in prod, or you could run into that scenario where you're opening the circuit breaker for things that are not truly errors. And it's critical to use the Hystrix dashboard. You want to have visibility into Hystrix. It works really well, and you could potentially have your timeout set too low or the tuning parameter set incorrectly. And if you don't have visibility, you're not keeping a close eye on your logs, or you have the Hystrix dashboard, you could be timing out commands that really shouldn't be timed out. So you definitely want to have the dashboard. And the dashboard has been really useful for us just for knowing when other things are happening in the system too. So a couple examples. One time we were going to a meeting, and in our office we have pretty much all of our TVs have Hystrix up, the dashboard up at all times. And so people become habituated to just always look at the dashboard as they're walking around the office or getting water or whatever. And we were going to a meeting, and we noticed that we were getting like 3 or 4% timeouts on some of our commands, which is higher than normal. And it's not enough to have any real production issues, but it was more than we would normally see. And so we decided, well, we should sit down and figure out what's going on. So we talked to our ops guys, and we said, hey, we're starting to see some timeouts in prod. Are you guys doing anything? And they said, yeah, we're doing upgrades and doing rolling restarts on all the servers. And so it was really cool. Like, they were surprised that we knew that they were doing that. And we had really good visibility. We've also seen like garbage collection pressure, where we have like search indexes that kick off, and we see lots of small objects that get created, and so now the garbage collector starts pausing, and we'd see timeouts in Hystrix. So it's been really useful for us, and we've gotten a lot of insight, even using the percentiles and finding out how long some of our code was running. So the dashboard, personally, I wouldn't ever use Hystrix without the dashboard, because I think it's very risky. All right, so that's everything I had.